SWE-agent. Agent-computer interfaces enable automated software engineering. Preprint. Princeton Language and Intelligence. Abstract. Software engineering is a challenging task requiring proficiency in both code generation and interacting with computers. In this paper, we introduce SWE-agent, an autonomous system that uses a language model to interact with a computer to solve software engineering tasks. We show that a custom-built agent-computer interface, ACI, greatly enhances the ability of an agent to create and edit code files, navigate entire code repositories, and execute programs. On SWE-bench, SWE-agent is able to solve 12.5% of issues, compared to the previous best of 3.8% achieved with Retrieval Augmented Generation, RAG. We explore how ACI design impacts the agent's behavior and performance and provide insights on effective design. 1. Introduction. Language models, LMs, have become helpful assistants for software development, with users playing the role of mediator between the LM and the computer to complete programming tasks. For instance, after executing LM-generated code, a user may request refinements from the LM based on computer feedback such as error messages. More recently, LMs have been used as autonomous agents that interact with computer environments without human intervention. This approach has the potential to accelerate software development, but remains largely unexplored in realistic settings. This work introduces SWE-agent, an LM-based autonomous system that can interact with a computer to solve challenging real-world software engineering problems from SWE-bench. At every turn, SWE-agent outputs a thought and a command, and then retrieves feedback from the execution of the command in the environment. As our main contribution, we establish the importance of designing an agent-computer interface, ACI, to enhance the LM agent's performance. We find that custom ACIs tailored to LMs can outperform existing user interfaces, UIs, such as the Linux shell designed for human users. Consider the baseline of using a Linux shell interface, which naturally lends itself to turn-based interaction with an LM agent due to its text-only input commands and outputs. In practice, we find that this is an unsuitable environment for agents. For example, it does not provide simple commands to edit a small chunk of a file and does not provide any feedback when invalid edits are made. We find that this substantially hampers performance. This leads us to construct a novel agent-computer interface for SWE-agent, which provides commands for viewing, searching through and editing files, along with carefully crafted environment feedback, including informative error messages for edits that contain syntax errors. We empirically show that these ACI elements substantially improve performance. When using GPT-4 Turbo as the base LLM, SWE-agent solves 12.5% of the 2,294 SWE-bench test issues, substantially outperforming the previous best resolve rate of 3.8% by a non-interactive retrieval-augmented system. We perform an ablation study on a subset of 300 SWE-bench test issues to analyze our ACI design choices, Table 2, and show that SWE-agent solves 10.7 percentage points more issues than the baseline agent that uses just the default Linux shell. Even though our ACI was developed for GPT-4 Turbo, we find the interface transfers to a different LM, namely SWE-agent with Claude 3 Opus, can solve 10.5% of issues. To summarize, our contributions are twofold. First, we build, evaluate, and open source SWE-agent, a state-of-the-art system that can solve real-world software engineering tasks. And second, we introduce the concept of the Agent-Computer Interface, ACI, and show how ACI design can lead to substantial improvements in the performance of LM agents without modifying the weights of the underlying language model. We hope our work can drive the community toward further research on autonomous LM agents and agent-computer interfaces, ACIs. 2. The Agent-Computer Interface. An LM acts as an agent by interacting with an environment through iteratively taking actions and receiving feedback. Typically, the environment is fixed, such as in robotics, where agents control actuators in the physical world. However, Digital environments offer the flexibility of developing an interface between the agent and the computer, reflected by the wide variety of interfaces for programs, application programming interfaces (APIs), and humans, user interfaces (UIs). Here, we argue that LM agents represent a new category of end users, and we call the interface they use to interact with computers the Agent-Computer Interface, ACI. Agents interact with a computer in a series of turns, iterating between the agent issuing commands and the computer responding with the command's output, visualized in Figure 2. The ACI specifies the commands available to the LM and how the environment state after the execution of each command will be communicated back to the LM. It also tracks the history of all previous commands and observations, and at each step manages how these should be formatted and combined with high-level instructions into a single input for the language model. In this paper, we keep the language model fixed and we focus on designing the ACI to achieve better performance. This means that we shape the available actions, their documentation, and the environment feedback to complement a language model's limitations and abilities. We use two approaches to enhance the ACI on a development set. We manually inspect the behavior of the agent to identify difficulties and propose improvements, and we run a grid search over ACI configurations. This leads us to several observations on what makes for effective ACIs. 1. Actions should be simple and easy to understand. Many bash commands have documentation that includes dozens of options. Simple commands with a few options and concise documentation are easier for agents to use, reducing the need for demonstrations or fine-tuning. This is a defining principle for all SWE-agent commands covered in Section 3. 2. Actions should be efficient. Important operations, e.g. file navigation, editing, should be consolidated into as few actions as possible. Efficient actions help agents make meaningful progress towards a goal in a single step. A bad design is to have many simple actions that need to be composed across multiple turns for a higher order operation to take effect. We incorporate this into the editing and search interface designs covered in Section 3 and analyzed in Section 5.1. 3. Environment feedback should be informative. High-quality feedback provides the agent with substantive information about the current environment state and the effects of the agent's recent actions without providing unnecessary details. For instance, when editing a file, updating the agent on the revised contents is helpful. Figures 3a, 3b, and Table 2 provide evidence for this. 4. Guardrails mitigate error propagation. Like humans, LMs can make mistakes when editing or searching, but LMs struggle to recover from these errors. Building in guardrails, such as a code syntax checker that automatically detects mistakes, can help agents recognize errors and then fix them. We show the effect of editing guardrails in Table 2. We provide analysis and ablation studies in Section 5 to show how alternative interfaces affect performance. 3. SWE-agent, designing an ACI for software engineering. SWE-agent uses an ACI that enables an LM to act as a software engineering agent. To evaluate our system, we use SWE-bench, a benchmark for evaluating LMs on real-world software issues collected from GitHub. SWE-bench's issue resolution task reflects an important responsibility of software engineers. Given a codebase and a natural language request, feature request, bug report, generate a code-based revision, i.e. patch, that passes unit tests which verify the issue has been remedied. Solving these tasks requires performing a number of software engineering subtasks, including bug localization, program repair, and writing tests. Existing application interfaces to perform software engineering have naturally been designed around the human user. For instance, developers frequently use GUI-based IDEs, such as VS Code, or screen-based text editors, such as Vim. These interfaces have rich visual components and feedback that make them powerful tools for humans, but may not be as suited to LMs. Consider a text editor like Vim, which relies on cursor-based line navigation and editing. Carrying out any operation leads to long chains of granular and inefficient interactions. Furthermore, humans can ignore unexpected inputs, such as accidentally outputting a binary file or thousands of lines returned from a grep search. LMs are sensitive to these kinds of inputs, which can be distracting and take up a lot of the limited context available to the model. On the other end, commands that succeed silently confuse LLMs. We observe LLMs will often expend extra actions to verify a file was removed or an edit was applied if no automatic confirmation is given. We show that LMs are substantially more effective when using interfaces built with their needs and limitations in mind. SWE-agent overcomes these challenges by introducing powerful, tailored tools to provide agents with a simplified interface to the computer, i.e., the Agent-Computer Interface, ACI. A well-designed ACI should help the agent understand the state of the repository given the previous changes. It should also help the agent recover from mistakes, remove unnecessary context from prior observations, and suppress any unusual, lengthy program outputs. SWE-agent provides an ACI for LMs to act as software engineering agents, allowing them to effectively search, navigate, edit, and execute code commands. SWE-agent does this through the careful design of the agent's search, navigation, file viewer, file editor, and context management. Our system is built on top of the Linux shell and allows access to common Linux commands and utilities. We describe the components of the SWE-agent interface in greater detail below. Search navigation. Navigating codebases requires finding the right file and content that is relevant to your purpose. The common strategy for this is to look up terms that might be useful, like files, functions, or class definitions mentioned in an issue. We introduce special commands, find file, and search dir, that output a summary of search results when searching for file names and strings within files or directories. Examples of these search result formats can be found in Figure 8. The find file command can be used to search for file names in the repository, while the search file and search dir are used to locate strings in a file or the files of a subdirectory, respectively. Our interface encourages efficient searches by suppressing verbose results. The search commands return at most 50 results for each search query. If a search produces more than 50 results, we do not report the results and instead suggest to the agent to write a more specific query. File viewer. Once models have found a file they want to view, they can do so by using the interactive file viewer by calling the command open on the file path they want to view. The file viewer presents a window of at most 100 lines of the file at a time. The agent can move this window with the commands scroll down and scroll up, or skip to a specific line with the go-to command. To facilitate in-file navigation and code localization, we display the full path of the open file, the total number of lines in the file, the number of lines omitted before and after the current window, and the line number appended to each line visible. An example of this interface is shown in Figure 3a. File editor. We provide a few commands that allow models to create and edit files. The edit command works in conjunction with the file viewer, allowing agents to replace specific ranges of lines in the open file. The edit command takes 3 required arguments: the start line, the end line, and replacement text. In a single step, agents can replace all lines between the start and end lines with the replacement text, which is visualized in Figure 3b. After edits are applied, the file viewer automatically displays the updated content, allowing the agent to observe the effects of its edit immediately without needing to invoke any additional commands. An example agent response, including a file edit, is shown in Figure 3b. Similar to how humans may use tools like syntax highlighting to alert them of format errors when editing files in an IDE, we integrate a code linter into the edit function to alert the model of mistakes that may have been introduced when editing a file. Errors from the linter are shown to the model with a snippet of the file contents before and after the error was introduced. Invalid edits are discarded, and the model is asked to try editing the file again. Context management. The SWE-agent system uses informative prompts, error messages, and history processors to keep agent context concise and informative. Agents receive instructions, documentation, and a demonstration on the correct use of bash and ACI commands. At each step, agents are instructed to generate both a thought and an action. Malformed generations trigger an error response, shown in Figure 15, asking the model to try again, which is repeated until a valid generation is received. Once a valid generation is received, past error messages are omitted except for the first. The agent's environment response display computer output using the template shown in Figure 14, but if no output is generated, a specific message stating your command ran successfully and did not produce any output is included to enhance clarity. To further improve context relevance, observations preceding the last 5 are each collapsed into a single line. By removing most of the content from prior observations, we maintain essential information about the plan and action history while reducing unnecessary content, which allows for more interaction cycles and avoids showing outdated file content. More on the implementation is provided in Appendix A. 4. Experiment setup. Datasets. We evaluate on the SWE-bench dataset, which includes 2,294 task instances from 12 different repositories of popular Python packages. We report our main agent results on the full SWE-bench test set and ablations and analysis on the SWE-bench Lite test set unless otherwise specified. SWE-bench Lite is a canonical subset of 300 instances from SWE-bench with a focus on evaluating self-contained functional bug fixes. Models. All results, ablations, and analysis are based on 2 leading LMs, GPT-4 Turbo and Claude 3 Opus. We experimented with a number of additional closed and open source models, including Llama 3 and DeepSeek Coder, but found their performance in the agent setting to be subpar. Many LM's context window is too small, such as Llama 3 with a context window of 8K. GPT-4 Turbo and Claude 3 Opus have 128K and 200K token context windows respectively, which provides enough room for the LM to interact for several turns after being fed the initial set of system issue descriptions and optionally demonstrations. Baselines. We compare SWE-agent against 2 baselines. The first setting is the non-interactive Retrieval Augmented Generation RAG baselines established in Jimenez et al. 2024. Here, a BM25 retrieval system is used to retrieve the most relevant codebase files using the issue as the query. Provided these files, the model is asked to directly generate a patch file that resolves the issue. The second setting, called Shell Only, is adapted from the interactive coding framework introduced in Yang et al. 2023a. Following the intercode environment, this interactive baseline system asks the LM to resolve the issue by interacting with a shell process on Linux. Like SWE-agent, the model prediction is generated automatically based on the final state of the codebase after interaction. Metrics. We report % resolved as the main metric, which is the proportion of instances for which all tests pass successfully after the model-generated patch is applied to the repository. We also report the average cost metric, the average API inference cost incurred from running SWE-agent on a task instance for successful instances. Due to budget constraints, we set the per instance budget to $4. If a run exceeds this budget, the existing edits are submitted automatically. Configuration choice. During the design process of SWE-agent, we arrived at a final ACI design through qualitative analysis of system behavior on a small set of hand-picked, easier examples from the development split of SWE-bench. For the remaining hyperparameter choices, we perform a hyperparameter sweep over the window size, history processing, and decoding temperature. Further description of the configuration choice is provided in Appendix A. 5. Results. Main results. Across all systems, SWE-agent with GPT-4 Turbo yields the best performance, solving 12.47%, 286 of 2,294 of the full SWE-bench test set, and 18% of the light split. We present several empirical ablations that quantify agent-computer interface design's effect on task performance. We provide insights on language agents' behavior and common failure modes. 5.1. Analysis of interface design. Following Section 3, we perform several ablations of the SWE-agent interface, specifically with respect to the SWE-agent with GPT-4 setup. The performance of each ablation relative to the SWE-agent with GPT-4's performance on SWE-bench Lite is denoted by the red arrow. Our case studies shed light on interesting agent behavior along with the impact of different ACI designs. Human user interfaces are not always suitable as agent-computer interfaces. Current LMs are vulnerable to a number of pitfalls when searching for relevant content in the shell-only environment. Some exploration patterns, e.g. chains of CD, ls, cat, are extremely inefficient. grep or find lookups can be better, but occasionally produce many lines of irrelevant results. We hypothesize that better localization is possible with faster navigation and a more informative search interface. Figure 4 compares the shell-only setting with two different search interfaces. Iterative search, directly inspired by traditional user interfaces for search, such as Vim or VS Code, shows results one by one via the file viewer. Agents can look up results using next and prev actions. Each result displays the matching line along with n surrounding lines of context. An advantage is that an agent can begin editing directly after seeing the relevant code in its search. However, when given a large number of search results, agents tend to look through every match exhaustively, calling next until each result has been inspected. This inefficient behavior can exhaust an agent's cost budget or context window, leading to performance even worse than shell-only setting. Compact, efficient file editing is crucial to performance. SWE-agent's file editor and viewer is designed to consolidate the editing process into a single command that allows for easy multi-line edits with consistent feedback that automatically updates the agent's view of the file after editing. In the shell-only setting, editing options are restrictive and prone to errors. The primary methods available are either replacing the entire file through redirection and overwriting, or utilizing utilities like sed for single line or search and replace edits. Both methods have significant drawbacks. Redirection involves copying and rewriting entire files for even minor changes, which is both inefficient and error-prone. Although sed can facilitate specific edits, executing multi-line edits is cumbersome and can lead to unintended consequences that are challenging to detect. Moreover, both strategies lack immediate feedback about file updates, making those silent operations potentially confusing for models to interpret and increasing the risk of errors. Without SWE-agent's file editor interface, performance drops. We also find that agents are sensitive to the number of lines the file viewer displays. Both too little content or too much leads to lower performance. Guardrails can improve error recovery. A prominent failure mode is when models repeatedly edit the same code snippet. The usual suspect for this behavior is when an agent introduces a syntax error, e.g. wrong indentation, extra parenthesis, via an errant edit. As discussed in Section 3, We add an intervention to the edit logic such that a modification only applies if it does not produce major errors. We compare this interface with a shell-only and no linting alternative in Figure 5. This intervention improves performance considerably. 5.2. Analysis of agent behavior. Consistent problem-solving patterns emerge when LMs are equipped with useful, intuitive ACI. In this section, we discuss several model behaviors and problem-solving patterns that can be discerned from model performance and each model's corresponding trajectories. Reproduction and/or localization is the first step. SWE-agent usually starts a problem by attempting to write reproduction code and/or localizing the issue's cause to specific code based on file names and symbols referenced in the issue's description. This is reflected in Table 3 and Figure 6, where 4 of the most frequent patterns involve performing such diagnostics. To reproduce, models will create a new file, add reproduction code to it with an edit, then run with Python. Localization happens both in the absence of and after reproduction, using file names and symbols referenced in the issue's description. Agents will then invoke search_dir, search file, and find file to identify the root cause. In Figure 6, the distributions for the first 4 turns strongly correlate with these trends. Table 8 further corroborates this observation by showing the most frequent patterns per turn. A majority of turns are spent editing. From turn 5 onwards, the most frequent 2 actions from all turns are edit and Python. We show a normalized view of Figure 6 in Figure 13 for easy comparison. The dominant pattern, also captured in Tables 3 and 8, is a repetition of editing a file followed by running the original reproduction script to check if the change has the intended effect. For turns 8 to 16, submit is the third most invoked action. From manual inspection, our conclusions are that agents rarely deviate from this pattern, but they rarely recognize dead ends or reset their problem-solving approach. Agents succeed fast and fail slowly. We find that runs submitted relatively early are much more likely to be successful compared to runs submitted after a large number of steps or cost. We show in Table 10 the distribution of resolved and unresolved instances, including only instances that did not exhaust their budget. We observe that successful runs complete earlier and at cheaper cost compared to unsuccessful submissions. Overall, successful instances solved by SWE-agent with GPT-4 finish with a median cost of $1.21 and 12 steps compared to a mean $2.52 and 21 steps for their unsuccessful ones. Further, we find that 93% of resolved instances are submitted before exhausting their cost budget. For these reasons, we suspect increasing the maximum budget or token limit are unlikely to lead to substantial increases in performance. 6. Related work. 6.1. Software engineering benchmarks. Code generation benchmarks, which evaluate models on the task of synthesizing code from natural language descriptions, have served as a long-standing bellwether for measuring LM performance. Subsequent works have built upon the code generation task formulation to contribute new benchmarks that translate problems to different programming languages, incorporate third-party libraries, introduce derivative code completion tasks, increase test coverage, change the edit scope, and add robustness to dataset contamination. Code generation problems are largely self-contained, with short problem descriptions, around 100 lines, and corresponding solutions that are similarly brief, requiring nothing more complex than basic language primitives. Tests are either handwritten or generated synthetically via fuzz testing. In recent months, rapid development of LMs has begun to saturate many of these benchmarks. The top method scores 94.4% on human eval. Gauging future trends with the code generation task paradigm may be limited by the simplicity of this setting and the cost of human-in-the-loop problem creation. In response, recent efforts have demonstrated that software engineering, SE, can serve as a diverse, challenging testbed for LM evaluation. Repository-level code editing introduces many reasoning challenges grounded in real SE subtasks such as spotting errant code, identifying cross-file relationships, and understanding code-base specific symbols and conventions. As a field, SE has generally studied tasks in a more isolated manner. Prior benchmarks tend to frame problems in isolation from the rest of the codebase. We use SWE-bench because it unites many separate SE tasks such as automated program repair, bug localization, and testing under a single task formulation that faithfully mirrors practical SE. Furthermore, SWE-bench task instances are diverse, having been collected from real GitHub issues across 12 different repositories. In addition, SWE-bench performance is based on rigorous, automatic execution-based evaluation. 6.2. Language models as agents. The co-emergence of stronger LMs, increasingly challenging benchmarks, and practical use cases have altogether motivated a paradigm shift in LM's inference setting. In practice of traditional zero or few shot generation, language agents, which use LMs to interact with a real or virtual world, have proliferated as the default setting for web navigation, computer control, and code generation tasks. Interaction and code generation are increasingly used together, with code as the modality of choice for actions, tool construction, and reasoning. Code language agents have also been applied to offensive security, theorem proving, and clinical tasks. To the best of our knowledge, SWE-agent is the first work to explore language agents for end-to-end software engineering, SE. A key observation we noticed when designing SWE-agent is that many interactive methods, which perform well for rudimentary code completion tasks, do not work for more general settings like SE, a trend also exhibited by baselines for difficult math and competitive programming benchmarks. SWE-agent's takeaways are a reliable indicator of the robustness and scalability of agents' ability to reason with code. In addition, prior works tend to independently explore the merits of tool use, prompting techniques, and code execution in interactive settings. Agent-computer interface design accounts for the sum of these factors under a unified framework and introduces the idea that crafting LM-centric interactive components has meaningful effects on downstream task performance. 7. Discussion. We introduced SWE-agent, a language agent for software engineering that achieves state-of-the-art performance on SWE-bench. Through our design methodology, empirical results, and analysis, we demonstrate the process and value of designing agent-computer interfaces, ACI, tailored for agents. We release our code, prompts, and generations, and set up the code base to allow for easy extension to new commands and feedback and agent history formats. We hope that SWE-agent will serve as a foundation that inspires future work towards more versatile and powerful agents. Beyond various empirical applications, we hope the further study of ACIs could also make principled use of and contribute to our understanding of language models and agents, analogous to the synergy between human-computer interaction, HCI, and psychology. Humans and LMs have different characteristics, training objectives, specialties, and limitations. And the interface design processes can be seen as systematic behavioral experimentation that could reveal more insights into these differences and establish a comparative understanding of human and artificial intelligence.